Enough. Okay. So it should be recording now. So thank you very much for the invitation. And so what I want to do today is talk about some of the problems I've been looking at for the last couple of years and hopefully excite people who have knowledge of how to use machine learning to try to look at some of these. And so I'll focus on two specific problems. There's a bunch of other ones in number theory that I believe are very accessible. We have a lot of results right now on the theory side, but there is a lot more that can be done, a lot of really interesting lower order patterns that can be seen. If I had had time, I'm on a backup computer right now, I would have actually put in something from the eclipse we just saw. So I actually watched totality with my daughter, and it was amazing. 99% of the sun is covered by the moon. And if you're just looking at it without glasses, you wouldn't see the moon at all. The main term is just completely dominating the lower order effects that are going on, and only when you look at things the right way. So I'm hoping for the people who have expertise in writing the code for machine learning that they can actually make some progress in some of these problems. So unfortunately, there's a lot of problems in number theory that we care about that have extremely slow convergence. I'll talk a little bit later today about some problems in elliptic curves. The convergence is on the order of the log of the conductors. So even if you're looking at something of size 10 to the 20 for the conductor, that's just absolutely terrible on a log scale. There is tremendous opportunities with improvements in computers, but we're not going to be able to go far enough to really see a lot of things kicking in. So I'm hoping that we can find some ways to sniff out some of these lower order terms. To just give you an example of just how bad the subject is, this is one of my favorite false theorems. 40% of all integers are prime and 20% of all integers start a twin prime pair. So I will prove this false theorem to you computationally. If you look at all the integers up to 10, there's 2, 3, 5, 7. So 40% of your integers are prime, and 3 and 5 both start a twin prime pair. If you doubt this, I will double the range of computation, and I will go up to 20. And again, we see 4 new primes, and we see again 2 more numbers starting twin prime pairs. So this is the danger of computation misleading you and trying to figure out for what problem you're looking at, what's the correct scale. And we would never make conjectures about prime numbers by only looking at things up to 20. But unfortunately, for a lot of things with elliptic curves and related problems, it's really equivalent to doing something like that. Just as a side note, I've mentioned numerous times, I'm looking for collaborators. I'm also one of the managing editors of the Journal of Number Theory. So we are extremely eager for papers in machine learning, especially with connections to number theory. So if you do have anything appropriate, or if you know people who might be working on something like that, please let us know. We also have some funding available to help support conferences. Okay, so I'm going to talk mostly about 2 papers that I've done with student researchers over the years. Both of these topics I love because they're extremely accessible, that you can get involved without having to know too much. Just the bare minimums of L functions is enough for a lot of what we're doing, and the bare minimum of some linear algebra. So I'll start off a little bit with classical random matrix theory. So I was a double geek as an undergrad. I had both a math and a physics major. My accent in speech is from growing up in Boston, but my accent in research is from learning my number theory from a nuclear physicist. And he was just sick and tired of having on the order of 1,000 data points. So I was like, wait, in number theory, you can get billions of data points in an hour? It was exciting. And so he started looking at zeros of the Riemann zeta function, related things, after looking at the energy levels of heavy nuclei for decades and just doing painful measurements to get on the order of a couple of hundred results. All right. So we'll assume some basic level of physics. If you have 1 point mass in the universe under gravity, it's boring. If you have 2 point masses under gravity, it's boring. Once you have 3 point masses in general configuration, this is now extremely interesting. And we cannot write down a closed form analytic solution. Well, if we can't do this for 3 bodies, imagine how much worse it is for something heavy like uranium with over 200 protons and neutrons. So the way physicists got an idea of what was going on is they would shoot high energy neutrons into the nucleus and see what would come out. One of the best quotes I've ever heard is, imagine you want to try to understand how a grandfather clock works. What you do is you take 2 grandfather clocks, accelerate them to about 99% the speed of light, smash them together, look at what comes out, and then deduce the internal structure of the grandfather clock from the collision. This is what nuclear physicists do, and I will show you later that this is actually what number theorists do as well. We use different language, but we essentially do the same thing, but a lot cheaper. So nuclear physics comes down to solving a problem from linear algebra. So HCN equals ENCN. So H is the Hamiltonian of the system. The CNs are the energy eigenstates, and the EN are the energy eigenlevels. There are only two things that prevent this from being a linear algebra problem that you would see in a standard class. The first is H is infinite by infinite. And normally when we teach linear algebra, we don't look at infinite by infinite matrices. And the second is we don't know any of its entries. So normally you would have some difficulty diagonalizing the matrix that's infinite by infinite without knowing any of the entries. So Wigner's great insight was basically to say, screw that, let's just do things more probabilistically. So imagine that we have a box, and for simplicity, molecules are moving just left or right. You can look at all possible configurations, and for each configuration, you can look and see what is the pressure on one of the walls at a given moment in time. And then you can average over all configurations and get some kind of system average. And the hope is that whatever system you happen to be looking at will be close to the system average. It is possible that all the air molecules of the room will congregate in one corner here, but we are not really worried about that, and we don't have contingency plans. I haven't seen anything from the AMS about something like that. The odds of that are so small, we don't really have to worry about that. The hope is most states are close to the system average. And then depending on what type of physical problem you're looking at, that might impose some kind of symmetries or structures on the matrix, on the H I was talking about a moment ago. And depending on those structures, the eigenvalues will have different properties. So going through a little bit of the details of the calculation, let's imagine we have a real symmetric matrix, so A equals A transpose. We can assume for simplicity that the randomness comes from choosing the element of the matrix from some nice fixed probability distribution P. In number theory, we don't really do this anymore. We use things like classical groups, Haar measure. There's a more natural notion for something like that to relate to number theory, but this is a great example and easy to work with. And there's a lot of interesting things that you can see. And for most problems, it doesn't really depend on what you choose for this P. I will say the probability of choosing a matrix A is just the product of the probabilities of the elements. And so, the probability that Aij is in an interval would be just integrating the probability measure over that interval, and then we take the product over all the independent entries. If the matrix is real symmetric, that's either the lower trigonal and then the main diagonal, or the main diagonal and the upper, whichever way you want to do it. And so we want to understand the eigenvalues of A, but it's the elements of A we know about. Well, one of the ways we can do this is we can attach a measure to each A as follows. So for each eigenvalue, I'm going to put a mass of size 1 over n. And since there are n eigenvalues, this will give me a probability measure. So I'm going to use the Dirac delta functional. So it's something that integrates to 1, and all of its mass is concentrated at x naught. So if I integrate any function against it, it just returns the value of the function at the point x naught. I'm going to divide the eigenvalues of my matrix by 2 square roots of n. The 2 is not that important. It's just so I can say circle rather than ellipse later. It's how do the eigenvalues depend on n that really matters? What's the correct scale to study things? And the square root of n, that's what really matters. So if I just integrate my density from A to B, that will count how many normalized eigenvalues do I have in that interval. If I want to calculate the kth moment, I would just integrate x to the k. It will return the eigenvalue to the kth power. And by the eigenvalue trace lemma, that's just the trace of A to the k. And we can begin to see now why there's a hope that we can actually make progress with this. The trace of A to the k is going to be a polynomial in the matrix elements. We know the matrix elements. So the hope is maybe we can calculate these kth moments. And the hope is that if your probability distribution is nice, if you know the moments, then you know the density. Okay, so if I give you a general real symmetric matrix with probability tending to 1, almost every matrix will have its eigenvalues close to a semicircle. And so, if I choose, for example, 500 matrices, I'll choose each entry to be a Gaussian 400 by 400. You can see very closely the fit with the red semicircle line, going through. Now, we have to do a little bit with the probability distribution. Without loss of generality, I can always adjust the distribution if it has a finite mean and a finite variance so that it has mean 0, variance 1. And then it's a game of how much do you want to impress your friends in terms of what do you want to assume about the higher moments. If you assume maybe it's like the 3 plus epsilon moment is finite, I think that might be enough to get the results that you need. Or you can just say, I'm going to just be nice. I'm going to just assume all the moments are finite. If the first and the second moments don't exist, then you can actually get very different behavior. So the Cauchy distribution is a great one where you can argue as to whether or not it has a mean. It clearly does not have a variance. The probability is decaying like 1 over x squared when you multiply by x squared. That's clearly going to give you an infinite second moment. And you can see that the distribution of normalized eigenvalues is not going towards a semicircle. And the blocks at the end are just all the eigenvalues that large or larger. All right. So as I mentioned, the key ingredient was the eigenvalue trace limit. This is what allows us to get our hand on the eigenvalues by relating what we want to understand to something that we know, the entries of the matrix. And we'll see an analog of this in a little bit when we get to L functions. So to get a sense of what the right scale is, we can just use the eigenvalue trace lemma when we take A squared. And so then the trace of A squared is the sum of the eigenvalues squared. So it's going to be the sum of Aij, Aji, it's the sum of Aij squared. Since we're assuming everything comes from a distribution with mean 0 and variance 1, the second moment is the same as the variance. So we expect each Aij squared to be of size 1. We have n squared of them, so we expect this sum to be of size n squared. So we have n squares of eigenvalues that sums to something of size n squared. So each eigenvalue should be roughly of size square root of n. So this really simple calculation tells you that as the matrix grows, we expect the eigenvalues to be growing like the square root of n. If you actually want to start to prove things, we then have to just integrate and find what the kth moment is. We would have this polynomial, the trace of a to the k, hitting the product of the probabilities, and then we have to roll up our sleeves and we have to do the integration. And depending on the structure of the matrix, the contributions will become very interesting. It will depend on a lot of interesting stuff from algebraic geometry, from topology, from combinatorics. There's a lot of stuff that's going on. To just give you a completely misleading sense of how easy the calculations are, one of the things we can do is we can look at the second moment. So we would have the sum of Aij squared, and when we look at all the products, the only one that's going to really matter is when Aij squared hits the corresponding probability. So I'll pull that one out over here. All the other ones, I'm just integrating a probability distribution, which is just going to be 1. I've chosen this to have mean 0, variance 1. So this will just be 1. So the whole calculation becomes 1. It gets a lot harder when you go beyond the second moment. When you start looking at the general moments, you have to then figure out which ones match in pairs. And so this is what one of my advisors called counting on your fingers. If you ever have something that is unmatched, since we're assuming the mean is 0, if it's unmatched, it will just integrate to 0. So everything has to be matched in at least pairs. And then it turns out if anything is matched in a triple, you lose a degree of freedom and it doesn't contribute. So everything has to be matched in pairs, but not every pair matching is going to contribute the same. Okay, what I love is these become accessible problems for young people. Maybe not extremely young, but definitely college age students are young enough that they can look at problems like this. And so we heard a little bit about Go, and I think we heard about chess, but we have not heard about checkers. So I did use checkerboard. I should have probably just updated the slide to a chessboard rather than a checkerboard. But again, this is not my standard computer. It's working right now, and I don't want to risk doing anything on this computer until after the talk is given. So let's look at the following interesting ensemble. So what I'm going to do is I'm going to take a checkerboard, and normal checkerboard is, you alternate every square, but maybe I'll alternate every 3 squares or 4 squares or 5 squares. And what I'll do is, here I'm going to alternate every 3 squares, I'm going to put a W, either for Williams College where I teach or for weight, whichever one you want to view. And then every other entry will be chosen, randomly as before. And I will assume that, I have a real symmetric matrix. And then the question becomes, what impact does this have on the eigenvalues of the matrix? And the reason I'm interested in stuff like this is I'm trying to search for interesting behavior. I want to have some parameters that I can play with. Later this summer, I'm going to hopefully have some of my students look at some generalizations of this as to what might happen if the W's don't have to be the same, but are actually just the same on each diagonal. This would give me a Toeplitz matrix. Maybe there could be some interesting interpolations between the structures of the two. Everything I'm going to talk about now are things that I can prove theoretically, where I can actually isolate the lower order terms. I think there's a lot of interesting stuff going on for these related ensembles, but I don't know how to get at them. And this is why I'm hoping to try to interest people in the machine learning community, that if you're interested in this, or if you have any students who might be interested in this, I think there's some interesting ensembles we can look at and then try to figure out what the behavior is. Humans are really good at recognizing patterns. This is why we have the Are You a Robot test, and we are very good at detecting, where's the bicycle, where's the crosswalk, or whatnot like this. I think we can definitely see that there are 2 classes of eigenvalues for this 2 checkerboard matrix, 100 by 100. And so it turns out that this is 100 trials. For every such matrix, almost all the eigenvalues have size square root of n. there are two eigenvalues that have size n. Unfortunately, as you look at the higher and higher moments, if we want to try to understand what is the distribution of the eigenvalues, the two eigenvalues of size n, as you get to the higher moments, completely overwhelm the contributions from the n-2 eigenvalues of size square root of n. And they make it impossible to get any information about what's going on in the both, even though that's where almost every eigenvalue is. You can't use the method of moments anymore if you want to analyze what's going on here. Those small little two things completely overwhelm. Now, in this case, I don't need machine learning to figure out the pattern. I can easily identify what's going on and we can prove results. But there are a lot of related ensembles where, what if this blip was not separated? What if this was a lower order blip living inside here? Could you notice that there is some structure going on in lower order terms that's being masked by the main term? And that's what I'm really trying to get people excited about. And so here I'm just increasing the size of the matrix, and you can see that the eigenvalues, it's still about the same number, and it's moving further and further to the right as I increase the size of the matrix. And as we keep going, it just goes further and further to the right. And we can even try to figure out theoretically what's going on by putting in an appropriate weight function. And so it takes a while to figure out what is a weight function that I can work with analytically. What's nice about this function is from 0 to 2, it's non-negative. Actually, it's non-negative everywhere, but it's really close to 0 near 0. It's really close to 1 near 1. And so when I use this weight function, it's going to only give me a contribution, if I want, for those eigenvalues that are far out in the extreme. And I can, of course, do a modified thing and just focus on the stuff near 0. And just to give you a sense of just how quickly it goes, this is looking at n equals 4 to the m. Already when I have 4 to the 5th, you can see it's extremely peaked near 1, and it will just localize to what's happening there. It turns out that the distribution of those eigenvalues is an interesting function of the size of the leaps in the checkerboard. And these turn out to agree with other well-known distributions in random matrix theory. So we were able to isolate, we were able to prove what they were. My hope is that we can find similar stuff in other families. Okay, what I want to do now is I want to shift to talking a little bit about L functions and about some lower order terms where, again, I think there is some tremendous opportunities for people who are interested in machine learning. And if you have some students who have good coding skills, I've got a bunch of problems that I think would be very accessible. So just to make sure we're all on the same page, here is the famous Riemann zeta function. It's defined as the sum of 1 over n, where n ranges over the integers. And by the fundamental theorem of arithmetic, you can write every integer uniquely as a product of primes in increasing order. So I can write it as a product of primes. One of the reasons why this is so useful is this is 2024. What is the next integer after 2024? Next integer after 2024. 2025, right. It's actually very easy to find the next integer. We don't need machine learning. We don't need anything famous. We even have an explicit formula for the nth integer. Everything about the integers, their spacing, it's well known. Primes is much harder. What is the next prime after 2024? No, the next prime. No, the next prime after. Yes. So I teach problem solving. I'm often the point person for button. You need to know what is the next prime number, because a lot of times in competitions. So 2027 is prime. And I believe 2029 is also prime. But you're much harder to figure out what the next primes are. And so the hope is that by knowing what the integers are, we can use that to give us information about the primes. Just as a fun fact, if you haven't seen it before, if I take the limit as s goes to 1, the sum of 1 over n to the s becomes the harmonic series which diverges, which means there must be infinitely many primes. And you can even use this to get some sense of how quickly the primes grow. Another fun one is if you take s equals 2, you get pi squared over 6. Pi squared is irrational. If there were finitely many primes, then the product over primes would be rational. And so since pi squared is irrational, there must be infinitely many primes. You can use this to get some estimate of how quickly the primes grow. It is, if people are interested over lunch, I can share, it is the result of the worst paper I've ever written in my life. I will leave it at that for now. All right. So it turns out that the Riemann zeta function satisfies a functional equation. So if you know its value at s, you know its value at 1 minus s. It is conjectured that all the non-trivial zeros have real part 1/2. So we can write the zeros as 1/2 plus I gamma. Instead of looking at the Riemann zeta function, we can look more generally at L functions, where instead of 1, we put something AFN. You can put anything you want. The question is, when is it going to be something useful and worth studying? So typically, we might have the AFs coming from something with geometric interest, maybe elliptic curve, something like that, which we'll talk about later. We believe as long as you still have an Euler product, that the Riemann hypothesis will still be true, and we can still write the zeros as 1/2 plus I gamma. And there's a nice correspondence now between this and the nuclear physics I mentioned earlier. So with nuclear physics, we have the spacings between the energy levels. If the Riemann hypothesis is true and all the zeros lie on the line real part of S equals 1/2, there might be a correspondence between how the zeros are behaving and how the energy levels in certain nuclear physics ensembles are. And there's a lot of conjectures about this. If you can prove these correspondence, if you can find a physical system whose energy levels are the zeros of the Riemann zeta function, you will win every prize in math and physics that is not age limited. And if it's age limited, they will give you a plaque. They've already established that precedent with Wiles and the proof of Fermat's last theorem. So these are extremely important problems in both of the subjects. So for today, I want to focus on elliptic curves. One of the nice things about being a postdoc at Brown is you get to know Joe Silverman, who is kind enough to give you the images from his book. So this is, the standard. Has everyone seen elliptic curves? Or should I quickly go through elliptic curves? Everyone has seen elliptic curves? Okay, so you can form a group structure on them, and we can use this to construct an elliptic curve L function, where we're going to basically count how many points are there mod p. So looking at all pairs x and y, such that it solves y squared is x cubed plus ax plus b mod p. And then it turns out it's good to look at p minus the number of solutions. So if you look at things naively, well, if I put in any value of x here, half the time it's going to be a perfect square, and that should give me 2 roots. Half the time it should not be a perfect square, and that should give me 0 roots. Well, there's also, it could be 0, but 0 gives exactly 1 root for y. So you might expect that on average, you should have 1 solution for every x. You would expect this to be of size p. So I'm looking at fluctuations from what I expect. So this is just a really good way to normalize things. And we can use this to build a L function. And one of the big conjectures is if you look at the order of vanishing of this L function at s equals 1/2, then that equals the group of rational solutions to the elliptic curve. So it turns out that we can put on a group, and that group can be written as some number of copies of z plus a torsion part. The number of copies of z is equal to the order of vanishing of this. There's a lot of properties of primes that are related to zeros. I'm not going to go through these because this is not a number theory talk. I just want to give a quick sense of how we attack problems like this before getting into the open problems. So in complex analysis, one of the Pavlovian responses you get whenever you see a function is you take its logarithmic derivative and then you do a counter integral. And so we take the Riemann zeta function, we take its logarithmic derivative, and because we can write our zeta function as a product over primes, well, the log of a product is the sum of the logs. And this is why it's so important that we always have this always have this product expansion for our L functions. We want to be able to do calculations like this. So the derivative of the log of the product is going to be, I can always interchange things because I can just wave my hand like this, and of course it can be justified, is going to be the same as the sum of the derivatives of the logs. We then use the geometric series formula to expand the denominator, and then all that really matters is the first term. The other terms turn out to be much smaller and you can handle them. And now when I do my contour integral, if I integrate against x to the s over s, when I shift my contour, I'm going to get a contribution from the pole of the zeta function, which will give me an x. And if all the zeros are less, those will give me something of size x to the 1/2. And then over here, I'm going to get this weighted sum of log p. And this is essentially the prime number theorem. And so it turns out that this is an indicator function. It's going to be 1 if p is less than x. It's going to be 0 if p is greater than x. So we'll only count the primes up to x. It'll count them with a log p weight, but we can always remove log p weights without too much trouble. Instead of integrating this against x to the s over s, I could integrate it against more generally some test function p. And so now I'll have p to the s, p to the minus s. Well, if I just replace that with an exponential, you can see that what I really have is I have the Fourier transform of phi over here. And so I can replace this logarithmic integral, which as I shift contours will give me phi at the pole and then phi at the zeros, with an integral of log p against phi half at things related to the primes. And so this leads to an explicit formula, and this is the analog of the eigenvalue trace lemma. This is the starting point of all these investigations. This is what allows us to get our hands on this. it relates a sum over the zeros to sums over primes, prime squareds, and higher and higher and higher. It turns out once you get to the prime cubes and higher, it doesn't really matter when you do the expansion. These are lower order terms. I don't want to go into too much detail about the cationic density conjecture. What I basically just want to say is that for a general L function that we're looking at, we have some kind of expansion of a product of what's called stochastic parameters. And we have an explicit formula very similar to what we saw a moment ago. The sum of my test function at the scaled zeros is related to this kind of expansion over here. And when I try to do this calculation, all that really matters, it turns out, are the first two moments. The other moments don't really contribute to the main term. They contribute to lower order terms. This is very similar to what you have seen in the central limit theorem. Why do we have so much universality when we keep adding a random variable to itself? Well, you can always adjust so that the mean is 0 and the variance is 1 if your distribution is nice. So you don't really see the shape of a distribution until the third or the fourth moment. And when you look at it, that's why we have the universal convergence. That's why it's going to the Gaussian. Very similar thing is happening here. The main term is completely governed by the first and the second moments of the stochastic parameters, which are essentially universal, and the higher moments only affect the rates of convergence. I'm going to skip the details. Just to finish off the circle, this is the dictionary to convert from nuclear physics to number theory. In nuclear physics, you study energy levels. In number theory, we study zeros. In nuclear physics, you get information by shooting in a neutron and seeing what comes out. In number theory, we shoot in a Schwartz test function. That's our feat. In nuclear physics, you can only put in a neutron whose energy is in a certain band. The sums that come out that we need to evaluate, these integrals of phi hat, then evaluate them at primes, and then sum them over the primes weighted by the coefficients of the L functions, we, turns out, can only evaluate these prime sums if our test function phi hat is suitably restricted. So that is the analog of the energy, and it only gives us some information about what's going on in the zeros. So again, this could be another opportunity for machine learning. We can only do these calculations theoretically in certain windows. All right, so what I want to do now for the last 20 minutes or so is talk about the bias conjecture. So I've been looking at this since I was a graduate student. I have not found a counterexample, nor have my students. I am amazed at how carefully I phrased things as I was a graduate student, that it has survived so long. I was careful enough to cover my ass, yeah, the kid's not here, okay, to protect myself against certain possibilities. I am very hesitant, though, about whether or not this is true in general, because I was trained as a theoretical mathematician. So I am only able to prove theorems. So this is related to number theory, right? Oh, my training, or this yes. The bias conjecture is related to number theory and to the stuff I've just set up. And all of the data that I have on it is theoretical data from families I can work on. And the families I can work on are very special families where I can do the calculations. And so I'm very concerned that we're getting well, I'll say a biased view for the bias conjecture by only looking at these families. And this is where I think machine learning has some real opportunities. So a one parameter family of elliptic curves is going to be something of the form y squared is x cubed plus atx plus b of t, where a and b are polynomials with integer coefficients. Every time I choose a value of capital T to be an integer, I specialize and I get an elliptic curve. And I want to look at the oth moment of the quantities we were looking at a moment ago, basically p minus the number of solutions mod p. And the hope is that if I understand the oth moments, I can understand a lot of things that are going on. For a lot of problems, it's only the first two moments that really matter, in terms of just trying to understand the main term behavior of the zeros. For some things, the higher order moments will actually matter as well. They'll give you some corrections in the rate of convergence to the main things. It turns out that some of the lower order terms in the second moment have a lot of implications for things going on in number theory. Since this is not a number theory talk, I'm not going to really emphasize that right now. But even though the first two moments control the limiting behavior, the lower order terms of how you have the first and the second moments have incredible consequences. So Rosen and Silverman proved that if you assume a bunch of nice things, which we assume are true, then the first moment is related to the rank of the elliptic surface over Q of T. So rather than looking for solutions in the integers, I take the original elliptic family and I look for solutions x of t, y of t where x and y are now polynomials or rational functions of t. And what they showed is that if you calculate, essentially the first moment, multiplied by log p, divide by p, divide by x, in the limit, that's going to converge to the negative of the rank. Now, what's nice about this is if I can jerry-rig a family where I can actually calculate the sum on the left, I can actually use this to sniff out the rank of the elliptic curve. And there are ways that you could actually numerically prove it. You could actually do height matrix calculations that can be done in a reasonable amount of time. But if I can actually evaluate these sums, I can actually determine the rank. And so it becomes an interesting way to construct families with given ranks. The second moment is more interesting. So Michel proved that the second moment is of size p squared, and then the next terms keep going down by a factor of square root of p. There's cohomological interpretations for where they come from. It is possible to have a term of size p to the 3/2 that doesn't vanish. And for understanding the zeros, the main term is the one that matters the most, but the other terms do have impact as well. And so trying to understand all of the terms in the expansion is quite important. The bias conjecture that I came up with when I was a graduate student is the largest lower order term in the second moment expansion, which does not average to 0, is on average negative. So for instance, I could have a term of size p to the 3/2, which averages to 0, and then a term of size p, which is maybe of size negative p. So this is where I was very careful. So imagine I have a term of size p to the 3/2, which half the time is p to the 3/2 and half the time is negative p to the 3/2. That would average to 0, so I would not consider that term. I now go to the p term, and imagine the p term is negative 2p half the time and positive p half the time.
This depends on t, so within t, so that means this averaging is done on the instances on realization of t or big T or not.
Okay, so for a given special, so I'm looking at what's going on over the family, and so I'm averaging over all t at a given moment, and then the number of t you average over is going to be growing with p. And so it is possible that you could have a term that's of size plus p half the time and minus 2p half the time. So it would still be on average negative, even though for half the primes, you would actually be getting a positive bias. And in fact, that's what I'm going to be reporting on in just a little bit, that actually does happen. So it doesn't have to always be negative for the first correction term. It just has to be on average negative. What makes this so difficult, and this is where I'm hoping machine learning can help, is that a lot of times there are terms of size p to the 3/2, and then I believe there's a term of size p that's negative on average, but the term of size p to the 3/2 is just overwhelming the data, and I just don't know the right way to look at it, except in very special cases where you would have to be a moron not to see it. And I don't think anybody here is a moron. I think when you see the pictures later today, you will agree it's pretty easy to see the pattern.
Do you have any sense of what the size is average negative?
I don't. I mean, I think it's on average maybe like an integer times p. I think that there might be.
You're saying the center of that strip is basically now shifted on the left on the real line.
Mm-hmm.
Right? I mean, it's not 0, but it's shifted.
Right. Yes. But again, since the main term is of size p squared and we have fluctuations of size p to the 3/2, the shift is going to be getting smaller and smaller and smaller because I'm dividing by p to the 3/2. And that's what makes it so painful, is my shift is of size 1 over square root of p, which is getting very small, and it's going to be just drowned out in noise from the main term. Now, where I'm hoping that machine learning can be of assistance is I think there's actually some structure to this main term noise that might be doable. All right, so to date, I've only been able to do the calculations in closed form for very special families, and because the families are very special, they have additional properties, so they may not be truly generic. I'm not going to talk about the details of how this comes into play with the lower order effects for the zeros. So here's the main ingredient. So I can actually write down my elliptic curve coefficients by using the Legendre symbol. So the Legendre symbol is 1 if x is a square mod p that's not 0. It's -1 if it's not a square, and it's 0 if x is 0 mod p. And by using that, we can see, oh, that's going to precisely count how often is this a square. If it's a square that's not 0, there should be 2 values of y that correspond to it. So if I want to understand my coefficients, I just have to understand these Legendre sums. If I want to understand the second moment, I would have to take this sum and then square that sum. Unfortunately, while we know how to do linear Legendre sums and we know how to do quadratic Legendre sums, we cannot do cubic sums in general. We don't have a good closed form expression. We don't know how to do it in general, which is why the elliptic curves are so difficult to study. I can write down a sum for the elliptic curves, but I can't compute it. But I can convert linear and quadratic. So the hope is that if I look at a family and I have this t to average over, I can somehow jerry-rig things so that in t, I have a linear or quadratic sum that I can evaluate. And then once I do that, I now have my sum over maybe x1 and x2, and maybe those are no longer going to be cubic. Maybe I can now jerry-rig things so things are going to be nice. And it turns out that that is the case. So I'm going to skip constructions. So this is probably the most important slide of the talk. So I'm looking at a bunch of different families of elliptic curves, and then I'm reporting on the first moment and the second moment. And so you can see all these families, rank 0, rank negative, rank 1, rank 2, and then the second moments. And all the families we've looked at, the second moment is always negative on average. And here, I'm not really seeing any positive and negative things that I'm worrying about. One of the more interesting ones is in the main list, the third to the last, the y squared is x cubed plus tx squared plus 1, where I have this term of size c3 halves p. And c3 halves p is the sum of p times the sum of x mod p of 4x cubed plus 1. Well, the sum of 4x cubed plus 1 on p, that's actually the coefficient of an elliptic curve. It's an elliptic curve with complex multiplication. So this coefficient here is just p times an elliptic curve with complex multiplication. So there is structure here, but it's not an easy structure to see. It's not the structure of it's a nice polynomial. And so to make progress on this, we would need to have a massive training set of data coming from a bunch of things in number theory, where we're trying to figure out what could these lower order terms be. I think some of it might depend on what is the prime congruent to mod powers of 2 and 3. Now, I think if you go up to 72, that might be enough, but in elliptic curves, there's often some difficulties if you 2 or 3, so pull those out, break things up like that. But the fact that this is not a nice polynomial, one of them it's p squared minus 2p minus 1. I can easily pick up a polynomial like that. But a polynomial where one of the coefficients is related to how often is 2 a cube root mod p, and then here is a coefficient of a specific elliptic curve with complex multiplication. There is a nice structure which we found. How much do we have a structure like this for other things? Here is a term of size p to the 3 halves, and we can actually write down explicitly what is it. Are there other formulas like this in the other families where we're seeing noise of size p to the 3 halves? And can the computer help us identify what they might be? There's just so many things to try. So as I said, we know linear and quadratic sums. We can try to actually calculate them for a specific family. So if I choose, one family here to just give you a sense of what can be done, if x is 0 or negative 1, the sum is clearly going to be 0. There's a typo on the slide. If x is not 0 or negative 1, this should be a x plus 1. I just multiply t by its inverse, and now I have a nice simple linear sum which I can evaluate. And I get that this will vanish. If I want to do the quadratic case, and try to find the second moment, now I would have to square it. So I'll use x and y as my 2 variables. Nice is, again, of course this is nice. This is the one I can do. I can just keep pulling out the x plus 1, y plus 1, and now I get a sum of t plus x and t plus y. This is a quadratic sum in t. We can do this quadratic sum in t. And it turns out that the sum is going to be p minus 1 if x equals y and negative 1 otherwise. Oh, well, when x equals y, this becomes really nice. This is going to be, something of degree 4, but it's going to be a really nice thing of degree 4. It's going to be x squared, x plus 1 squared. Well, as long as x and x plus 1 are not 0, those are just going to be 1. And so these quartics reduce actually to just being constants. And so this is what I mean about jerry-rigging things so everything comes out nice. I'm going to skip going through some other, families. You can do the calculations. There's lots of results for lots of different families. And then I want to just end with, let's see. I'm going to get something here. So I was, speaking at a conference at ISOM last July, and I told my students, as long as you give me this stuff at least 2 hours before my talk, I will report on what you're able to do. And so they had a really hard deadline, and they really took me up on the 2 hours. And they basically were getting me stuff just beforehand. So I've actually just used this quote in another paper that I'm writing in sports mathematics. If your experiment needs statistics, you ought to have done a better experiment, Ernest Rutherford. So there are 2 different data sets here. The second one is shifted down by -110. And again, just looking at it, it's hard to tell that there's a little bit of a bias in the second one. We need grid tests. Now, again, if I just calculate the mean, I can easily see the bias here. So this is what I meant by, I don't really think I need to explain much for you guys to see the pattern here. I think the pattern is pretty clear that something is happening, right? And so if you look at all of these coming down, there's something going on. Now, it's great that I was following your talk where you said the computer did not know the degree. But when you plotted it, it was perfectly understanding that the degree is going on here. There is something similar to the degree going on here. It's what is the prime congruent to mod 1. And so if you look at all the primes that correspond to the values on this line, those primes are all going to be congruent to 2 mod 3. And so here is everything else, the primes that are 1 mod 3, here are the primes that are 2 mod 3. There's something going on there. And it turns out we can actually analyze what's going on for the primes 2 mod 3 exactly. It turns out you can just send t cubed to t. It is a isomorphism when p is 2 mod 3. It's not an isomorphism when p is 1 mod 3. And so for this particular family, the t cubed becomes a t. It's now a linear quadratic. It's now a linear Legendre sum. We can now evaluate it exactly. And that's why we can get these formulas and we can get the nice decay. In the general case, we are just out of luck. We do not know how to prove what's going on here. I would love to know, is there some kind of expansion? What can you say about the low order terms? There's definitely something of size p to the 3/2 present, but what is it? Does it have any nice arithmetic structure? And again, I think there's a lot of problems like this. It doesn't have to just be coming from elliptic curves. There's a lot of things similar to this where there is, I believe, structure lurking, and we just need ways to learn it. And I'm here trying to get different communities to talk to each other. That there's a lot, I think, that can be done. So then we could just go through and try to find just different ways to plot things and see what's going on. So trying to look at, is there a large enough bias in the primes that are 1 mod 3 that's negative to overwhelm the small positive bias we know that's happening for the primes that are 2 mod 3? And it's definitely looking like there is a negative bias. I'm looking at the running average of the biases over here. And then in the next one, I'm looking at the running averages of, I believe, everything. Yes. Now, what is interesting is it does look like it does slightly break into the positive zone for ever so briefly. And so it would be interesting if the bias conjecture has to be then modified to, most of the time it will be negative, but occasionally the running average could become positive. I was very vague in what I meant by on average, the average is negative.
So what was the reason for this particular family of curves?
So basically I was just telling my students, explore as many families as you can. And so I had 6 students. They weren't quite running in parallel, but close to it. They were broken up into different groups, looking at different families and trying to see which ones were promising. And so it was a combination of numerical exploration and some theoretical coding to try to get a sense of which families might be interesting. And then once we had the interesting families, what kind of properties might be going on. And so the fact that we have this isomorphism t to t cubed means things become very nice for half the primes. And that's why we could evaluate those. But for the primes that are 1 mod 3, it's unclear what's going on.
Is there something special if you focus on subfamilies that are complex multiplication?
I don't know, because again, this family does not have complex multiplication. I don't think so.
Well, it depends on t.
If you take t equals 0, it would have complex multiplication. But other than that, for general t, I don't think it would have complex multiplication.
And there are families which have subfamilies which have complex.
Yes.
And is there something special for this?
For this one, I don't think that's what it is. There was another family which, when you were looking at the second moment, that's where the complex multiplication was entering.
But I was wondering just the
right.
the original family. If you looked at a family of curves with t's that are complex multiplication.
Right. or maybe, you know, the subfamily of squares within where maybe T is a square, is that might have some additional nice properties. I don't know. I mean, it's a good question to see if there are subfamilies within this, where you look at things that are 1 mod 3 for the prime. In these subfamilies, can you handle those cases? For the general case, we can't handle it. And so, you know, what my hope is that you know, anybody, especially if you have some students who are looking for projects, if they know machine learning, is can we start assembling a database? There are a lot of databases out there. There's the L function and modular form database, where there's a lot of information. We need some kind of interface to train the computers to look at all the stuff like this and then try to sniff out the patterns that's going on. So I don't know if number theory has everything set up as nicely as other subjects for these training programs, but I think this could be a infrastructure project that would be well worth the investment. So thank you.
Questions?